Now in this part of the video, we're going to discuss the thin lens equation. Just remember, in a thin lens equation, we have two types of lens. They are convex lens or converging lens with a positive focal length, and concave lens or diverging lens with a negative focal length. To understand more about the thin lens equation, let's assume that we have a convex lens. Remember that the horizontal line drawn in the center of a convex lens, or we can assume that we have a concave lens also, is what we call the principal axis line. And also we have the center to identify the focal length, or the distance from point F to the center of the lens. Now remember that focal length has the same distance with the other side and always appeared in both sides of the lens. Now, if we place an object, we have what we call the distance of an object to the center of the lens. And remember that distance of an object will be positive if the real object occurred, yet it will be negative if the virtual object occurs. Now, if we have a distance of an object to the center of the lens, we have also the height of an object, which stands for HO. If we have an object, we have also the image of an object, which is commonly occurred to the right side of a principal axis. Now, the DI is the distance of an image, and DI is positive on the right side, then the real image was formed. But if the image formed on the left, then DI will be negative and virtual image will occur. Now, if we have the height of an object, we have also the height of an image. Now remember, if the object and image exist in an upward direction, then our height of an object or in the height of the image will always positive. But notice that we have a downward image, which our HI will be negative. So if our height of an object is opposite to the height of an image, then the image is inverted. If the image is taller than the object, then the image was enlarged. Then if the image is smaller than the object, then the image reduced. Now for the formula, we're always using the thin lens equation, where 1 over f, or the focal length, is equals to 1 over the distance of an object, DO, plus 1 over the distance of an image. If the magnification naman, we're going to use the height of an image over the height of an object. But if we have no value between that two, we're going to use the negative DI, or the distance of an image, over the distance of an object to find our magnification. Now we're going to have an exercise. Now, if we have the converging lens, with a focal length of 6 cm and place an object away from the lens with a distance of 8 cm left, having a height of 2 cm. Where is the image located? How tall is the image? What is the magnification? Now, notice that 6 cm is positive because the converging lens occurred in the problem. Now, our distance of the object is equal to 8 cm and the height of an object is 2 cm. So, as we use this equation, now 1 is equals to the focal length, which is equals to 6 cm, equals to 1 over 8 cm, which our distance from the object, plus 1 over the distance of an image. Now, let's find the distance of the image since we have no value of di. Now, to solve the problem, we're going to find the lowest common denominator. Now, in this equation, we're going to use the 6 times 8 times di to find the solution of the problem, and multiplied each fraction in a parenthesis. So 6 times 8 times di times 1 over 6. Now we're going to cancel the 6. Now the remaining number will be 8 di. So 8 di times 1 will be 8 di is equals to 6 times 8 times di times 1 over 8. We're going to cancel the 8. So the remaining product will be 6 di. So 6 di times 1 will be 6 di plus 6 times 8 times di. So since we have the di in a third fraction, we're going to cancel the di's. Now 6 times 8 is equal to 48 times 1 will be 48. Now 8 di is equals to 6 di plus 48. Now remember, we're going to use the 6 di or the second fraction of a parenthesis to find the distance of an image. So 6 di minus 6 di will be 0, and 8 di minus 6 di will be 2 di. Now 2 di is equals to 48. We're going to cancel the 2 because we're going to divide each value to 2. Then the product will be the dividend from each fraction will be di is equals to 24 cm, and it is in a real image because di is equals to positive 24 cm. So if the real image occurs, then the image found in the right side of a lens in a principal axis. Now to find the magnification, we're going to use the negative di over do because we have no value yet to hi. So negative 24 cm over 8 cm, the magnification will be negative 3. If the magnification is negative, then the image is inverted. Now we have the value of negative 3, which in a magnification. So negative 3 is equals to hi over 2 cm. We're going to distribute we're going to cross multiply each fraction. Now, negative 3 over 1 is equals to height of an image over 2 centimeter. Then, the product will be hi is equals to negative 6, which if we ignore the negative sign, it is 3 times taller than the real object, and negative stands for the direction of an image. So the direction of an image is negative, then it was in a downward direction. Now, to make it more clear, we're going to draw a graph. So, in what you notice in this graph, the height of an object is opposite to the value of height of an image, which is what we call the image is enlarged, and also inverted because our object is in an upward direction while the image is in a downward direction. Now, another problem, we're going to use the diverging lens with a focal length of negative 4 cm and place an object away from the lens with a distance of 12 cm left, having a height of 2 cm. Now, where is the image located? How tall is the image? What is the magnification? Same as the exercise 2, but we're going to use the diverging lens. Now, as we follow the equation, 1 is over 2 negative 4 equals to 1 over 12 plus 1 over di. So, now to find the solution, again, from the problem, we're going to use the lowest common denominator, which is equals to 12, and distribute again in each fraction of the parentheses. In a parenthesis, I mean, so 12 di times 1 over negative 4 will be negative 3 equals to 12 di times 1, so 12 divided by 12 will be 1, so that will be stand for di plus 12 di times 1, so let's cancel the di since we have the di in a denominator, and it will be equals to 12. Now, our product of the equation will be negative 3 di equals to di plus 12. So, as always, we're going to use the middle value of the equation. So, di minus di will be 0, and negative 3 di minus di will be 4, negative 4 di. So 4 di minus 4 di equals to 12 minus 4 will be negative di equals to 3. And we're going to cross multiply, then di is equal to negative 3. So if the virtual image occurs, then the image found in the left side of a principal axis. To find the magnification of the diverging lens, we're going to use again the negative di over do which is equals to negative times negative 3 over negative 12. The magnification will be 1/4. And we're going to use the equation to solve the height of an image. So 1/4 is equals to height of an image over 2. Cross multiplication now will be 2 is equals to 4hi. Now 4hi will be divided to 4 to find the height of an image. So 2 over 4 is equals to 4hi over 4. Then it will be 1/2. Now remember, the decimal point of a 1/2 is equals to 0.5. Then our height of an image is equals to 0.5, which is smaller than the height of a virtual object. Now in this graph, notice that our image now is in the left side of a principal axis, and it is in upright because the height of an image is in the positive 0.5, and also reduced because the height of an image is smaller than the height of an object.